What we're going to do today, unfortunately our speaker for today developed a virus or something last night and canceled. So what we're going to do today is have Kris Pister and his group talk about Open Wireless Sensor Networks, OpenWSN, which is a very good talk. I'm glad to have him come and fill in. But before we get started, I wanted to introduce a visitor to the lab. It's Soichiro Hosodo, who is from one of our new member companies, Toshiba. I'm pleased that Soichiro and Rakesh Sethi, who's sitting in the back there, will be coming to our seminars for quite a few weeks now on Thursdays and beginning to interact with us, look at ways that we can work with Toshiba, get a better sense of what the Swarm Lab is actually doing, looking at ways we can hook in with projects at Toshiba. So I wanted to let Soichiro introduce himself so you would be familiar to when he comes around to talk with you. So please.
Yeah, nice to see you all. My name is Soichiro Hosoda. I entered Toshiba 7 years ago, and I live in Japan. So last weekend, I reached California. And so I didn't prepare a slide, but in this morning, I picked up 2 slides. So, I'm an engineer of designing hardware, especially media processor and circuits for car automotives and also cell phone and so on. And 2 years ago, I made a circuit for automotive car and driver's assistant. The circuit's name is Visconti 2. And this is a slide of ISSCC lab presentation. And our circuit is used in this car for these applications. Nowadays, the car includes many circuits and electric devices, and to embody this kind of applications. So front part is traffic sign recognition and pedestrian detection and forward car collision warning. So, and in the car, drivers monitoring sleeping or boring, and back side is back over prevention, and side is lane change assistant. And so the application, these application needs image recognition. So our circuit is accelerating the processing. So our circuit consists of these architecture. And I designed multi-core. Multi-core includes 4 cores. Each core is built by media embedded processor, Toshiba original processor. And there are 4 SRAMs on circuit. And in gray color, these are hardware accelerators for these applications. And this is Affine accelerator for modify the at first there are 4 cameras, on front side 2 cameras and the back side 2 cameras. So from camera the image is distortion, and so we have to modify it to ideal image. So at first, Affine accelerator modifies the image to ideal images, and histogram and matching and cohort engine is needed for recognizing person and car line and in front car and the backside car. And the filter is needed to modify the image to easy to understand the ideal image. So also another interface is to communicate another circuit. So this platform is not only for cars. if you want to use, we can supply these platform to any applications. And yeah, I will develop next generation these circuits and so on. Thank you.
Kris,
Yeah, please.
This talk at some point. It turned out to be a bit of a last-minute surprise, so I ended up kind of taking a couple of talks and cramming them together. I'm going to start off and give the first 30 minutes or so, and then I actually have to run off to another meeting. And then Chavi is going to take over and talk about the details. So I'm going to give kind of a high-level overview of my view of how this works with a little bit of pointers to some of the work that's going on in my group. And then Chavi will say a lot more about the OpenWSN piece of that. So we're all used to the spectacular vision that Jan has laid out, and some piece of that goes back to the work that we did on the Smart Dust project a long time ago, and I've got the scars from the years between now and then that inform me of why, although I believe the swarm vision 100%, otherwise I wouldn't be here. It's not going to be easy. It's going to take a lot of work, and it's going to take a lot of hard work from people in the audience and others. So I'll talk a little bit about my experiences with taking Smart Dust into standards and show you some real applications, which are unfortunately few and far between in the world of wireless sensor networking these days. And that leads into OpenWSN, which Chavi will talk about. And then say a little bit about where we're headed on hardware and stuff like that. And then hopefully later in the semester, I don't know how many slots we have left, but I think it'd be great to get a bunch of students' talks crammed in. What is the status on our
calendar?
On the calendar? Do we have space?
We probably have 2 slots in November at
Okay.
this point. But yeah, having some student talks.
So I think it'd be great to have student talks from around the little short ones. Yeah,
That'd be lovely.
it'd be good.
The faculty need to encourage the students.
Well, that's yeah. Okay, so in '97 we wrote the Smart Dust proposal. Professor Bozer was a co-author, as was Joe Kahn, who then left for that junior university across the bay. And we made it work. It was a fun experience to get that mote on the tip of Lincoln's nose to actually talk. More importantly, I think, than the miniaturization of it, and other than just the sort of coining the phrase Smart Dust, which got people thinking about it, was when we built off-the-shelf wireless sensor nodes and started programming them. And the first multi-hop mesh we did was down what is now this hallway, used to be a different hallway in this building. And we made a 10-hop network from my lab over here all the way down to the Hughes room with terrible radios and the beginnings of software. That got the computer scientists interested. That got Randy Katz and David Culler interested. We wrote a joint proposal. David and I had a student, Jason Hill, who wrote the first version of TinyOS for his master's thesis, and that kind of launched the whole thing. And we put everything in the public domain, which I think was critical. And one demo that we did here was a very public demo that Richard Newton asked us to do to show that we could have some impact on energy consumption, because this was we had just had a summer where there were rolling blackouts in California because of the power situation. And Richard, the dean, was trying to sell Berkeley as the 4th of 3 IT center, or I forget what it was called, centers that Gray Davis was doing. And so he said, do something with energy. So we monitored temperature in all of the rooms on the 4th floor of Corey Hall. We put a mote in every single room, pretty much, in an afternoon, and brought that back. And for the press, we showed that we could simulate an electrical power emergency notification coming out of the California ISO, and we actually shed 100 kilowatts of load off of the roof of one of the giant chillers up there. And it actually all worked. So back in 2001. And we're still kind of recreating the things that we demoed for the first time in there. So everybody got really excited at that point, right? We were doing, there was so much excitement about where all the technology could go, and a bunch of startups coming out of MIT and other places. And the industry analysts were predicting this incredible acceleration. By 2007, the number of wireless sensor nodes was going to eclipse the number of cell phones sold on the planet, according to these guys. And so I was one of the people that jumped off and started a company, and did my best to get good celebrity endorsements for it way back when. But it turned out that this didn't happen. The reality is that in 2012, the number of wireless sensor nodes from a mesh standpoint, kind of the smart dust, tiny OS vision of what this ought to look like, is probably down here closer to single-digit million units. Not even up to this bottom bar, and that's all the way out here 5 years after this. So it wasn't that sensor networks took off, it was the industry analysts that took off. And what was it that stopped it? Well, this is an old survey, but the thing that was preventing people in 2005 when they were surveyed was reliability. It turned out that wireless for sensors has been out there forever. People have been trying to do this literally since the time of Marconi, but it's a real challenge. And getting the reliability, if you don't get the reliability, people will rip the system out and they'd rather not have intermittent data than having, or they'd rather have no data at all rather than have intermittent data. So, and power consumption's up there. Standards are important. That ended up consuming a huge amount of my life. But the thing that I find entertaining is, of course, what I set out to solve as an academic had absolutely nothing to do with what anybody in industry cared about. But also, as academia tends to do, right? We had this really hard goal, and it forced us to think about how to make ultra-low power systems, and that did have an important aspect to it. And since our systems were not very reliable, we had to think very carefully about reliability as well, but because they were so bad that if we didn't have good software and good algorithms on top of them, then they really wouldn't work at all. And so that turned out to be important. So I think this is the way university research often works. We're a little bit decoupled from the real problems, but we pick hard problems to work on, and we have brilliant students, and they go off, and on the way to solving a problem that may not be all that useful, they invent the technology or invent the solutions that end up being useful to everybody else. So what is it that you want from your sensory swarm, right? You want to be able to put it anywhere, and you want to get the data. Right? It's pretty straightforward. And I don't want to change batteries. I don't ever want to change batteries if I don't have to. So we came up with a handful, with an approach to doing this, building mesh networks, going back, and I'll show you some examples of this. And after long, long battles, and what's left of my hair turning gray, we ended up creating a whole bunch of standards. Most recently, the one I'm most excited about is this IEEE 802.15.4e standard based on time synchronized channel hopping. And the idea is that if you maintain tight time synchronization between nodes in the network, then they know exactly when to turn their radios on, and that lets them have much lower power. It means that you're not continuously chattering with your neighbors on a CSMA schedule and having chaotic collapse in your network. So it turns out means that you can scale the networks much larger, and it means that you can do frequency diversity. You can channel hop because everybody knows exactly what time it is. You know when you wake up what channel your neighbor is going to be on. So that turns out to be critical. Frequency diversity, spatial diversity, building real meshes, not building trees where every node and every link is a single path, a single point of failure. And simple idea, secure link layer act. This is another place where academia gets it wrong, right? Everybody who's ever taken a networking course knows that link layer acknowledgements don't have anything to do with end-to-end reliability, right? Therefore, this is stupid. Right? And that held academia back for a better part of a decade. It turns out if you don't do this, you don't have any end-to-end anything to get started with to know whether you're supposed to send the end-to-end DAC or not. So anyway, simple stuff. The core idea of this 802.15.4e is that every node in the network is time synchronized to something like a millisecond, probably closer to a microsecond these days. And so when B wants to talk to A has to wake up a little bit early. It knows it expects to see the packet from B start right there, but it knows that there's a little bit of error, plus or minus a millisecond or plus or minus a microsecond, something like that. And as long as B starts talking in there, then it hears the message, turns around and sends the ACK. And when it sees that first bit of B's packet, it knows what time B thinks it is. And so it knows what the error in B's clock is, and that information then can be sent back to B. So timing information flows in both directions with every packet transmitted. What does it take to transmit? This is current versus time. It takes energy to spin up the radio, and then you transmit the packet. Energy to turn around from being in transmit and fire up your receiver, and energy to receive that acknowledgement. And that basic quantum of charge that you pull out of the battery, the integral underneath that curve, tells you how long your battery is going to last, depending upon how long you do it. Back in 2003, that was 300 microcoulombs. When we first started shipping hard, it was 50. The best products on the market today are probably around 10, maybe 10 or 11. With the radios that have been made at Berkeley, in my group and Jan's group, we could get that down to under a microcoulomb. And that's and with the radio that Elad Alon's student just published, we may be able to get that down to under 100 nanocoulombs. And then things get really exciting, because then you can send an acknowledged packet 10 times a second for a microamp. And all sorts of fun things happen at that point. So a lot of times you're going to wake up and listen, and nobody's going to have anything to talk to you about. And anybody also who's taken a queuing theory class knows you'd better have more opportunities to receive than the actual traffic that's going through. So you wake up, you listen, and you go back to sleep, and that costs a certain amount of time. And again, today, something like 5 microcoulombs with commercial silicon, and probably you can get that down into the tens of nanocoulombs also if you do a really good job. So that's exciting for energy scavenging. So now I want to talk about some of the commercial deployments out there. There really are some. Wireless sensor networks is no longer an academic-only discipline. You do not have to write papers where you refer to the Great Duck Island deployment that we did back in 2004 or whatever it was. You can actually refer to things that happen in the real world. So this is what real companies like ABB are putting on their web pages now, is that they sell wireless sensors, that they come back through a gateway and back to a sort of a regular network and into plant information systems. So this is actually taking off. Adam sent me a link earlier today from InTech magazine that says this market is doubling. It said in the last 2 years it's doubled. I think it's actually doubling a little faster than that, based on my own experience. But it's definitely taking off. This is, again, almost 5 years old now, data of, or rather examples of things that are shipping. This is Emerson. They're one of the leaders in the space. And, they ship big chunks of stainless steel. It's not exactly smart dust. This is not going to be floating around in the atmosphere anytime soon unless you live on, I don't know, Jupiter or something. And they sell these for $1,000. And they sell about $1 million. Here, just to give you an idea, everything on here that has an antenna speaks wireless HART and interfaces with ABB devices and Siemens devices and GE devices, and all these multinational, multi-billion-dollar companies. They're all shipping products that actually interoperate for the first time in the history of the industry, by the way. All of the wired protocols previously were explicitly designed by the people who are pushing them so that they would not interoperate with the other companies' parts. So this is a huge revolution in the industry, and the result is that that's why it's taking off so fast. So here we are in the middle of the Saudi desert, and now on the north slope of Alaska, the same structure. You can see the antenna hiding underneath there, and the face of the instrument. You can't read what the instrument tells you, but it is in fact still transmitting that data. Here's one that it's in a rotating vat, so it gets, every 30 seconds or so it gets completely immersed. Still works. This one's talking about a mile away. So, it gives you an idea of range. As long as you're up on a tall pole, and you can go a long ways. Out in the middle of the North Sea, mobile, this is an old slide. It's over 1 billion moat hours of operation with maybe 100 failures in that time. So we're talking about something like a moat millennium, about 1,000 years is the MTBF.
What standard is it using now?
This is all wireless HART. So, and IEEE 802.15.4e takes the MAC layer of that and puts an IEEE label on it. And that's what OpenWSN is based on. So that's what my goal with OpenWSN was to take this stuff, right, which for the last 5 years, I've been watching these deployments work in the real world, and at the same time looking at what's coming out of academia and just shaking my head. You've got networks of thousands of nodes in the middle of the desert that perform far better than the 5 nodes sitting on the desktop that someone ends up writing a paper out. And there's just a complete disconnect between what people in academia are doing in the space and what's actually being deployed in the real world. And so the goal with 4E and all the other standard stuff I've done since HART was to standardize all this in a way that we could build a fully standards compliant stack from top to bottom in academia with open source implementations on multiple platforms and let everybody play with it. And so that's what Javi is going to talk about if I ever get off the stage. So here at Richmond, there's a wireless umbrella. Fabian, if he gets a chance later in the semester, will tell you about all the fun things he's putting in that. This is a fun deployment at a steel mill, 5% improvement in productivity. This is, well, okay, another fun example, monitoring bearings on rail cars, because if you don't find that the bearing is going bad and fix it before it dies, you end up with, pouring molten metal on the rails, which are made out of wood and creosote. If you go over a bridge, bad things happen. This is an interesting example where the mesh on each rail car comes back through a cell phone or satellite phone gateway. They've got both. They use the cell when they can and the satellite when they have to, back into the cloud, and then it's actually an SAP application that takes that and serves that to the customer. And that picture is coming up a lot now. So what are they doing? If you've got some distribution of failure times, you've got to bring that rail car in regularly to service it well below the mean. If you've got sensing on those bearings, you can service it much closer to the mean and reduce your service costs. Another one, rotating lime kiln, 5% throughput improvement. Why does that happen? Same kind of thing. You've got a distribution of how long it takes your product to cook. If you can't sense it, you've got to leave it in the oven for a lot longer. If you can sense it, you can take it out closer to the mean. Now, HVAC center monitoring the Met, monitoring the streets of San Francisco in this case. So if you drive around in the city, you'll see lane markers, and now they're actually drilled in and buried underneath the surface next to all of the parking spaces in San Francisco. Pretty much is like 8,000, at least in the core of the city. This is the actual mesh that is forming, and is colored according to what the signal strength is, or the packet error rate, more likely, on each one of these nodes. But it gives you an idea. And this is another one. They bring 250 motes back to a cellular gateway, which is powered, and then push that into the cloud and do all sorts of interesting things with it. Same kind of picture down in Los Angeles. So we're covering cities with these urban scale meshes now. And one of the neat things that you can do with it is you can actually do dynamic signage on parking and availability of parking and so on. So you can download the Parker app onto your iPhone, and it will tell you what the closest open parking space is to your favorite restaurant. And then you can pay for your parking and have a meter on your phone. And then when you stagger out of the bar at 2 a.m., it'll help you find your car on the way back. Branko Krkez, who also hopefully will be able to give us a talk later in the semester, working with Steve Glazer, has put a bunch of networks into the Sierras. And that they just got another $10 million, I think, to add more to those networks. So this is there's Branko working in a real-world environment up there with wireless monitoring. That if you can figure out how much water is in that snowpack and how dense it is and temperature and everything else, you can figure out estimate when that water is going to be available for either irrigation or power. And you can optimize. So people who like it for power want to keep it up there so that they can use it during the summer to help alleviate or sell it at maximum rates, if you want to be. And other people want to use it to water their plants. Anyway, so finishing up on that, where we started was very much proprietary networks and some network interface device on both sides of that, and the app was on separate devices. Where we're going now, after a lot of work on the standards, is that on a standards-compliant network stack, you can have your application there in an environment, in a real operating system environment, where you can write in C, and you can actually have a priority-based scheduler that you don't have to worry about all the things that are happening underneath you. You feel like you own the machine and still have some real-time capability for your sensor application. And then you just open a port, right? You pick an IP address and a port number, and you send UDP packets to that port on the internet. And it's all in native format in the network and native format to whatever database it is, whatever system it is that you're talking to. And that, I think, is a huge transformation in the industry and is really going to accelerate lots of other applications outside of industrial. So I won't say much about OpenWSN other than that we're trying to do multiple hardware platforms with multiple operating systems and have all of them interoperate with a single stack. 2.4 gigahertz, 15.4, this 15.4e layer to get you reliability and low power consumption, and then 6-low-pan UDP, and then CoAP is this HTTP-like thing on top. And as long as we demonstrate that, then let all sorts of other people play in that playground as well. Low-power radios. So part of the vision of Swarm is that these things become ubiquitous. Radios are still expensive today. Richard Su, one of my PhD students, graduated recently, showing that he could make a radio, terrible radio, but a radio nonetheless, using almost entirely standard cells and digital synthesis. And so this radio is pretty tiny. In 0.18 micron CMOS, it's a half a square millimeter. In 65 nanometer, it'll be a tenth of a square millimeter of CMOS. Terrible, right? From RF standpoint, 73 dB of link margin, awful. But in this room, that's plenty. And if you're looking for the ubiquitous swarm, right, there are plenty of people to hop to, plenty of other nodes in the network. 73 dB of link margin is all you need. And if you can drop that down in a tenth of a square millimeter, it gets to the point, it's not a whole lot larger than the size of the pads that you use for an SPI or an I2C interface or something like that. You just put a radio on there. Of course I'm going to put a radio on every chip I make. Another fun one, Ring Gina. So Ankur at some point is going to tell us about Gina. He's made this 9-axis guidance and inertial navigation board that's got a radio, microprocessor, and 9 axes on it. Joey is working with Ankur, printed little rings, and we're showing that we can actually monitor fingertips. There's Ankur eating pudding. So what's no, we won't get into that. And typing, and the whole goal of that goes back to a paper that I wrote with Seth Huller and a couple of other people back in '99, where we put accelerometers on the fingertips of a glove and used the acceleration data to see that you could actually type, you could use a virtual mouse and so on. And the goal was to get that down to a fingernail. I want to be able to have my wireless accelerometers on every fingernail and glue them on once a month or whatever it is. And then my computer, my cell phone, knows where my hands and fingers are all the time and exactly what they're doing. And so when I snap my fingers, I can type. I can type on my desk if I'm in the middle of a meeting. Or I can play air guitar or air drums or air whatever it is that CNMAT invents for us to do with that. Or anything else. I mean, for me, it's going to be typing in the shower, because that's where all of my good ideas come. Right? If I don't write them down there, I spend the rest of the day thinking, God, what was it? I knew I had a good idea. I swear I had a good idea. So how do we get there? How do I get to the point where I've got wireless accelerometers on my fingers? I've got to have power at that point. So Mike Lorek is working on doing very low power energy scavenging on chip. So you put a solar cell on chip, just standard PN junction, and make sure that you can take that low energy, hundreds of nanowatts potentially source, and DC to DC convert it up to a voltage that's actually useful for your electronics. Vivek Subramanian is interested in doing inkjet printed batteries on top of these things, so all sorts of fun things we think are going to happen there. And if you can do that, then my single chip moat, and by the way, right, your cell phone has a 3-axis accelerometer and gyro in it that are made with MEMS and CMOS integrally bonded together at a wafer level and then diced up. So we can put MEMS on that chip as well. So then you think about, what does it take to make a single chip moat in standard CMOS, possibly with this bonded layer on it like InvenSense uses. And you've got to get all this stuff on there to get it to work. Maybe not location. I'll say a little bit about that. And then you need an antenna. You need a crystal for the radio, a crystal for the real-time clock if you're going to do time synchronized stuff, and a battery today. Well, I didn't show you the papers that we've written on crystal-free radio, but for sure you can get rid of the real-time clock crystal with some on-chip intelligence. For sure you can get rid of the RF crystal. That's papers that we haven't written yet, but are known to be possible. For sure you can get rid of the antenna as long as you don't care so much about link margin. And if Mike gives us what he says he's going to give us, then we get to get rid of the battery as well. So now it's not minimal external components. It's literally zero. This thing, you dice it up and expose it to light, and it starts talking. So I mentioned location. I just want to show you one quick picture of that. These are the results of RF time of flight location with these 802.15.4 radios. This is the Stephen Lanzasera got his PhD with me showing that this was possible. That with a narrow band 2 megahertz bandwidth radio, that you could in fact get a few meter accuracy indoors out of these. His qualifying exam committee didn't believe him, by the way, until the very end of the exam. They finally passed him, but basically a couple of members who shall remain nameless said that this is impossible. So anyway, he showed that you could do it. Dust put it into silicon, so did NXP. So if you look, there's little green dots. There's 10 green dots throughout the space, largely on the periphery. Once you put up that, and they're just moats, they're battery operated. They also are time synchronized channel hopping, so they'll last for years on batteries. So you put the infrastructure in a matter of 5 minutes into this place, drag the green dots onto your map, and then the mobile devices wandering around in here, you can localize them. Not great. Certainly, especially not over here. This is the worst one. So inside the Faraday cage of an elevator, that was our worst guess. We thought the moat was all the way over there, and it was actually inside the elevator. But certainly in the cube farm area, in general, you're going to get it right. And for sure, you're going to know you're in cube farm, or you're in the lab, or you're in the kitchen, and you're not in this area, or you are over in that area. So localization, I think, is something that we can feed into our algorithms of the future. And so then finally, last slide, back when we wrote the smart desk proposal and started talking about what we wanted to do with this, there were a lot of people who didn't think it was possible. And I even had friends of mine say, I know what you're really trying to do. What? What am I really trying to do? I have no idea what I'm really trying to do. I wrote down what I thought I was trying to do. But now, a decade or so later, a little more than that, 15 years later, I think that we can teach it to undergrads. And my goal next semester is to have a project class where I get some of the best students from each of our undergraduate circuits and digital systems classes, and I turn them loose on the problem of designing this chip. We'll have some grad student supervision, hopefully get Mike's power supply in there and a couple of others, but basically design that completely integrated single chip moat in an undergraduate project. And see how far we get. I don't know. And I'm naively optimistic that we'll actually tape out at the end of the semester and have something that some of them will be able to test in the following semester. But that's where I want to go. And this guy, for sure, is going to end up running OpenWSN, because that's how you get reliable low-power communication through wireless sensors. So on that note, while Chavi is switching over, I'll take any questions, and then I have to run off. I've got another meeting that I've got to go to. But go ahead.
Great. Thank you.
So what kind of instruments are you going to make for us?
Responsible. I guess one question that always comes up is how often you sample. I mean, we are sampling our
touch-based interfaces at fairly high rates, and you're dedicated to fairly low-rate sampling. So it's a conundrum we'll have to resolve.
So I know, and you're talking about milliseconds, right? Is it kilohertz sampling rates, or is that?
Actually, we're up at a 10 kilohertz rate.
Okay, 10 kilohertz. So.
And I can argue why that's important.
No, I absolutely believe you. No, I know. We've had that discussion before. So Bernard maybe can comment on where the limits are on sampling accelerometers. And for sure, you can buy off-the-shelf accelerometers today, where at 10 hertz for 3 axes, they burn 3 microamps. And so, worst case, that goes up to 3 milliamps, and that's certainly stressful, but that's something that we can do for brief periods of time.
And I would say we're going for that high rate because we want to have some overkill at first to see what we can really bring it down to. So it's obvious that in many applications we're going to be satisfied with much lower rates.
Right.
But in general, when it gets less than a millisecond update rate, we begin to feel.
Okay. So then 300
later.
microamps, and now we're now as long as we're playing outdoors in full sunlight, then we're golden. So I can
Okay.
as long as I can be playing air guitar. It's just got to be under bright stage lighting.
All right.
All right. And on that note, I will turn it over to Chavi. I'm sorry.
One more question. I'm not going to let you off.
Hey, you were talking like it takes only a microcoulomb or less to do what, to send a packet?
Right. So today you can buy a radio or a product off the shelf that will burn just over 10 microcoulombs to transmit a packet and receive an acknowledgement to that packet.
What kind of a distance it can cover?
So that's the same radio that's in all those motes that I showed you that are in commercial deployment. So it can go, if it's on a pole on the middle of a snowfield, it can go a mile in Alaska. In this environment, you would expect, empirical hop depth of 1.5 probably in here. If you fill this area with motes and you put a manager anywhere in that corner or in the middle or whatever, most of them are going to be 1 hop away. Some of them are going to be forced to be 2 hops away, and some of them are going to send it on the 1 hop channel some of the time and on a 2 hop channel other parts of the time. So it gives you an idea. Indoors, that's, I don't know, what is that? But it's tens of meters. Outdoors, line of sight, well over 1 kilometer.
Amazing.
Thank you.
All right. Take it away, Chavi. Sorry.
Thanks, Chris.
Okay, hi everyone. Kris told all the secrets, so this will be fast. We work on OpenWSN, and what we do is an open source, standards-based wireless communication protocol stack using all the standards that can deal with low-power wireless communication. So as Kris shown, there are a lot of interesting applications for low-power wireless. I will not go into details because you already seen that. But the thing is that there are no current implementations of that standards that everyone can use. You can buy some radios on the market, but they have proprietary hardware, proprietary software, so you cannot modify, you cannot play with them. And we think that it's a good idea to develop that implementation, give it to the community, and see what happens. So we are developing that open source protocol stack based on these standards, and we are also porting that protocol stack to different platforms, commercial platforms that we buy or platforms that we do, like the ones I have here, and you can see later. Okay, this is Gina, that maybe Ankur talks another day about it. And this is our new mode. I let them here. You can look them after. So the idea is to go from the physical layer to the application layer. Okay, the physical layer is like the 15.4 standard that you can find commercial radios on the market. Also, Zigbee radios are running on that hardware and use that physical layer. On top of that, we implement a 15.4e that provides channel hopping and slotted communication.
And on top of this, we provide some services for neighbors discovery, knowing the schedule of the network. And we have the network layer that provides IPv6 connectivity using 6LoWPAN. 6LoWPAN is the same as IPv6, but as our packets are 127 bytes long, we have to compress headers. And then we keep compatibility, but we need a service at the edge node that converts from long 128 bytes addresses to some kind of addresses that can be transported in a packet into the network. Then on top of this, we have UDP, and in the application layer, we have CoAP. CoAP is another coming standard that is a compression of HTTP, and you can have REST interfaces to talk with modes as you have with HTTP. Okay. The challenges, as Kris already explained, are on the physical and MAC layer because we suffer from interference coming from Wi-Fi, from Bluetooth, because we are using the 2.4 gigahertz band. And so how we can combat these interferences? The first challenge is multipath. As you know, we can, if we look into a channel and we look the probability delivery ratio of packets, and we measure in a kind of a square of 20 by 20 or by 30 centimeters, we can see that in some places the PDR is quite high, 100%, so you send all the packets and all the packets are received. But in some places in that region, we have kind of valleys where the connectivity is very bad, and this is due of a multipath effect of the signals. So what we did is we measure all the channels in that band, and we saw that there's no correlation between them, meaning that if we change the channel at every packet, we mitigate the effect of a bad channel. Okay, and this is exactly what the 15.4e standard proposes. So we decided to implement it. Here we have the same example as Kris showed. Imagine that we have in these channels a lot of noise due to a Wi-Fi network, and we want to transmit all the time in that channel. We will have a lot of collisions or a lot of packet drops, but if in contrast we keep changing channel, we mitigate that effect. So 15.4e uses a slotted structure. This means that we divide time in slots, and each slot is used to transmit or receive, and the link is mapped into a kind of schedule table, and each link can have one or more of these slots. If we look inside the slot, we have some things that happen there. The objective is reduce the time that the radio is on, because we want to minimize the energy. So the secret is to have the nodes synchronized and know exactly when the packet will be sent, so the listener, the receiver, can listen just in that moment. So we keep synchronized, we keep the nodes synchronized, and then we have some special timing inside the slot. At the beginning of the slot, the radio is off, and the listener prepares to receive, the sender prepares the packet to be transmitted, but the radio is still off, and in a particular moment, the transmitter turns on the radio and sends the packet. The listener knows that moment, but because they can drift a little, has a kind of margin, and it turns on the radio a little bit before. This is normally one millisecond, and then listens for that millisecond. This is a waste of energy. And then it catches the packet, it receives the packet, and then we do exactly the same for the acknowledgement. Okay, so the secret is to keep synchronization between these 2 points on time. Okay, according to, if we have a network like that, we can schedule different links into the schedule, and we can have different objectives. For example, if we want that a link has more bandwidth, we can put more slots to that link. So here you can send more packets inside the frame. You also can improve latency on your network because you can schedule subsequent hops like one after the other in the schedule. And in that case, the packet will go in the one slot here, in the next slot will go to B, and then it will go to A. And with that, we improve latency. Or we can have robustness because we can schedule from one node more than one link, for example, from E to D, but also from E to C, and have multiple paths to arrive to the sink. And a combination of these techniques provides us the reliability we want. On top of 15.4e, we have 6LoWPAN. I already explained that we use that adaptation layer to compress IPv6 headers and have IPv6 addressing. And 6LoWPAN uses a routing protocol. It's called RPL. Both of them are standards, RPL and 6LoWPAN. And it's based on the gradient routing. This means that we have a sink with gradient 0, and all the nodes have the gradient to its gradient is calculated as the cost to transmit to its parent plus a metric, and normally the metric is computed as the number of packets transmitted divided by the number of packets acknowledged. It's a kind of quality ratio. And this builds a gradient, and you have multiple paths, so instead of having a tree, you have a mesh, which gives you the robustness you need. Okay, so this, so how OpenWSN evolved? We started with TinyOS, and TinyOS was an operating system that was that provided non-preemptive scheduling. It was using a component-based programming style, and it used also printf-based debugging. So these tools for us were a little bit scarce, and we wanted to improve a little. So we developed OpenOS. This is the operating system that makes now OpenWSN work. It's a non-preemptive scheduler, but it's pure C implemented, and we can debug with JTAG. And we are now working on the porting of our current protocol stack to FreeRTOS, which is a real-time operating system that provides multitasking, priorities, preemption, these kind of things. And we have some applications also running. We can monitor, we can send data to a server from each mode, and we can see them in the web browser. So we can have, these are the IPv6 addresses of the modes in a network, and they keep sending to our modes.x server, and we can see all their data, all using IPv6. We also can see all the resources that a mode has. So these are applications that are running in a mode. We can query the mode and see what kind of applications are running with the web browser, and just if we have, for example, one application that turns on an LED on the mode, we can click it from the web browser and turn it on the LED using also IPv6. And this is the hardware we were working on. We started with Telosb. You know that platform is a quite old platform that uses an MSP430 from Texas Instruments and a Texas Instruments CC2420 radio. We ported that platform to OpenWSN, so people in the world that has this platform, I think the academia has a lot of these, can just download our code and run it on that platform. Then the group developed Gina. The purpose of Gina was to fly helicopters, so it's a very lightweight platform with several sensors, and uses also the MSP430. This is a little bit more powerful than that one. This is 16 megahertz. The other one, I think, is 8 megahertz microcontroller. And after that, we decided to work on a new platform that it's here. It's the Open Mode that comes with a K20 from Freescale microcontroller. It's a Cortex M4 with a DSP, so you can do math inside. You have a floating point unit And it comes also with the Admiral radio, which is a commercial radio. And so this is our latest platform. And we did it in that XV form factor because we want that people using XV switches their radios for our mode and just downloads our code and can just have a better communication stack. Okay, here you have some more details on Gina, but I think that Ankur one day will talk about that. This is the features of open mode. It has 256 Ks of flash, 64 Ks of RAM. It has a 15.4 compliant radio. You can buy that radio. It has antenna diversity. And we have open source tools like Code Warrior to start developing, or you can use other tool chains like IR. And we also develop a mass storage bootloader. This means that when I connect one of these modes to my USB port, it appears as a flash USB drive. And I can drag and drop there the firmware, and it loads the firmware. So to program it is just connect it, drop the binary file, and it has the program on it. And as I said, it has this XV form factor. You can see here a picture. They are on the table as well. Also, you can find a lot of tools or add-ons to that platform because it has this XV form factor, and Arduino community is using that form factor. So we have a lot of tools, very cheap to play with, sensors. And we have a website where all this information is, you can find there. The most important thing is that our project is open source, so anyone that wants to use it can download the code, program the mode, and start sending packets. We have some tutorials as well, and if you have some problem with that, you can come here and I can show you some examples. Okay, and that's it.
You're in the first row, you start.
Yeah, so the hardware is available?
It's open hardware as well. So the schematic is on our website. You can download it and make it.
Oh, okay.
David.
I'm just curious, having been involved with the Tessellation OS in the PAR lab, and now I see TinyOS and this work, how do you see these OS efforts articulating one with another? And I've always thought, well, how can that big OS that Tessellation is fit on these swarm-like devices? That's my question. And Kubi isn't here.
And Kubi isn't here to take part. I think what he might say is that rather than trying to cram Tessellation on these small nodes, the question is where you do the subset and where you start to do the division of labor, because clearly these operating systems are designed for that platform, and that they have the code space, right? So Tessellation needs to talk to them, because clearly you need the system level operating system and the protections that Tessellation provides, but shoving that all the way down to the node is probably not a recipe for success. So I think that's a work in progress that Kubi's working on. He's trying to figure out. But that's a great question. Other questions? If not, well, thank you.